All right, and our next speaker needs no introduction, Jeff Bezanson. He's going to be talking about the state of trim.
Hi, everyone. Good to see you all. So I'm going to talk about the thing that everybody always asks me about, which is building binaries and building smaller binaries and this new trim feature that we have been working on. So I want to begin with a little history of us not building binaries, because that's something I know about. There is some relevant history. Yes, no binaries. Text only, please. So what things looked like in March 2011 was we had, note the command carefully, ls*.j. So this was all of the Julia source code that existed in the world at that time. And it wasn't even in a subdirectory yet. There was, pretty soon after this, we put it in a subdirectory, which is a great improvement. But, and the way the system worked was that one file start.j, every time you started Julia, it loaded that file, and that file simply included all of the others. So we just loaded all of the source code every time you started it up, which was okay when it was 200 lines, but it actually got to the point where it took about 10 seconds or so, and we actually lived like that for, I don't know, a couple of months or something. You actually had to wait 10 seconds for it to load and compile all of this code every time you started Julia. And that started getting very annoying. So we very quickly had to do something about it. So here, this is actually before even the public release, thank goodness, I put in this system image thing that you've probably all heard of. So the system image concept and terminology basically comes from Smalltalk and Lisp, where it's a very, very simple idea. And the idea is you basically just dump out the entire contents of the system and save it for later reuse. So the initial version of this was very, very primitive. I literally just traversed all of the data structures in the entire system and just serialized them to disk. And then the next time you started, we just deserialize it. And so that at least saves you all of the parsing and compiler analysis effort of putting all those data structures in place. So that basically solved the problem for a little bit of time. But this was a very primitive version of it. In particular, it only saved our data structures. It did not save the native code. So that was the next obvious thing to do. So a little while later, about 2 years later, Jameson comes along and he has these great understated commit messages, but a static compiling prototype. So, and what that meant, there's a longer message below that, but I had to cut it off here. But what that basically means is now we are saving and reusing native code as well as the other data structures inside. So then now we didn't have to regenerate that. So there's an improvement there. And then a couple of years later, we do the same thing but for packages, right? So before that, we were saving and reloading the kind of the base code, but packages you still had to load, totally separately every time. So eventually we got sort of the same thing that we had in 2011, but now for packages. So this is just very, very slow, laborious process. And then it even took a much longer time, an additional 7 years before we could save the native code for packages. And it was just very technically difficult to get that working, because when you have, pieces of native code do not like to exist in isolation because everything is referencing everything else. And so working out how to get the cross references between packages when you might be using different combinations of packages than we anticipated, and getting all the references to work and invalidating things that can't be used, and the logistics of it is difficult. So it took a while to get this working, but we did eventually, and that worked even better now. So one question is, why are we so weird about this? We're saving out about 4 different kinds of compiler artifacts at this point, and absolutely none of them are what people sort of really are used to or want from traditional languages like C or C++, like a small standalone executable or something about that. And the basic reason why we're so weird about this is traditional languages use this compilation model called separate compilation, where you look at a piece of code once on its own, save out a binary artifact, and then whenever you use it, you never look at the code again. You're basically not allowed to look at the code again. If you want to use that, you look at a header file. You can look at the header file again, and it tells you what's in there, and you go through that, but you never look at the code again. And we don't do that. We use more of what's called a whole program model, where we're always looking at all the code all the time. So when you use a library, the next time you call that library, we might look at all the code in it again, because we want to basically re-optimize it for whatever you're doing. So that has some trade-offs. It's very powerful in many ways. There are lots of powerful things you can do. You get certain performance properties that can be useful, but the trade-off is you get latency, and you get big binary sizes because everything is kind of together in one big blob. So, in some sense, the Unix system image is the entire contents of usr-lib, which is probably a couple of gigabytes. It's sort of, that's the Unix system image, so but we just put that in one file, like it's sort of what's going on, So the next kind of thing that happened, which is kind of a tangent that I'll just put off to the side here in this process of us trying to be normal about binaries, is that one thing we did along the way was make the compiler optional. So we at least had to decouple the large LLVM and our code gen system from the runtime. So it was at least possible to run some Julia code without the compiler because it's a really large dependency. So if you ever wanted to have a standalone binary, you certainly wouldn't want to be tethered to the entire compiler, which is probably more than 100 megabytes. So this has now happened. So we've been gradually setting the stage to maybe build some proper binaries. And now we are really getting there. So the most recent thing in this category is this trimming feature. So what is it all about? So basically the basic idea is we want to be able to get rid of the stuff you're not using. So my program only prints hello world. I don't need the other gigabyte of libraries. So we're going to remove all the stuff you don't need. So here's basically how it works. So you mark the entry points you actually need, the things you actually need that you want to call, or it can be implicit if you're writing an executable. Obviously, main is the entry point, so that's sufficient for that. Or if you're writing a library, you'll mark the points you want to be callable from a C ABI with @C_callable. And so then those become your entry points. And then you put this through JuliaC. We will try to prove what code is reached from those entry points. And in that process, you might get some compiler errors, because if we can't do it, we'll give an error, fix the errors, and then eventually you get a small binary. And the main use case for this these days is, well, by far the main use case is creating a library to be called from C, C++, Python. Much smaller use case as of now is executables, but that's obviously something people really want as well. And I should point out as part of this that a lot of times people wonder, oh, well, why not just use the precompiles? And it's actually very different from precompile statements because the precompile statements are sort of speculative. You're trying to sort of guess everything that might possibly be needed at runtime. And it's generally going to be way too much for these purposes. So in this process, we actually totally ignore precompile statements, and we just throw them out. And we only trace from the entry points that you specified just for this purpose. And the other thing that's interesting about it is the particular way it works. Is very specific. So you might think one thing you might want to do is try to prove what code is unreachable, right? Because if I want to delete some code, ideally I should prove that code is unneeded, and then it's safe to remove it. But that doesn't actually work, because it's very, very hard to prove that something is absolutely not needed. As long as there's one thing in the system that, well, maybe it might end up there, so I have to keep it. So that sort of puts the semi-decision on the wrong shoe, on the wrong foot. You need to do the opposite kind of semi-decision for the undecidable problem. And you need to only try to prove what can be reached. And anything else that I don't know about, well, I'm just going to throw it out and hope for the best. And it's going to be your problem, because the important thing is that we get a small binary. It doesn't matter if the binary works, but it has to be small. You see, that's how we've designed it. So a little more on that later. So here's just some examples of some things you might do. So if you want to write a library that's going to be called from C, you can do @C_callable and put C-compatible types for the inputs and the return, and that'll go in there. Or you can do this @main thing. So we had to add this because the name main was never special in Julia. If you say function main, that just defines a function called main. That's it, nothing else. So it would be breaking to do anything weird with main, so we added @main, which is, it defines a function, but then also says on startup this function is going to be called automatically. So it adds that behavior to this, which arguably we should have always had, okay, but we didn't, so we added @main, and it gets a string vector of the command line arguments. And as of now, it's supposed to return a C_int, just a C exit code. Maybe that's okay, I don't know, maybe it should be based on whether an error is thrown or something. Actually, if an error is thrown out of this, we will exit with code 1, so that sort of works already, but there's that. And all right, what if you do C-callable main? Well, you can actually do that as well. You can write C main and just put C-callable on it, and then that will be your C ABI main point. But then, of course, it has to use the correct C main argument signature. So you will get a C int and a char star star, and have fun with that if you really want to do that. So one thing that came up in this is, so basically when we do the trimming process, we give errors basically for dynamic dispatch. That's the easiest way to think about it, because at a dynamic dispatch, we don't know where the control flow is going to go, so we're not sure what to include and what not to include. That's the basic idea. But very quickly, that didn't really work very well for a lot of real-world code, because this kind of pattern is very common, where someone is doing just a simple, classic object hierarchy kind of thing, where there's some possible types, and then you have a vector of maybe some different types, and we do something to all of them. And this is a pretty common pattern, and it looks very general. It's just an abstract type with some struct subtypes. Well, that's pretty general, but there's some specific things about it that matter. So usually there's a small number of subtypes. It's not 1,000. It's probably like less than 10 or maybe less than 20 or something. And there's a method that has a concrete signature defined for each one. So that's also important, because inside each of those area methods, since the signature is concrete, those are probably very type stable and very statically compilable. So those are all sort of perfectly innocent, easy to compile methods. And so then if I call one of those, it turns out this kind of has to be allowed in some way, because there's just way too little code works with trimming unless you allow something like this. So is this allowed? And so yes, this is actually allowed sometimes. So basically it has to fit this pattern. There have to be kind of not too many methods, and they all have to be concrete. Then we will go through and compile all of them. So the question is, okay, what if there were 1,000 subtypes of it? Maybe you do actually want us to compile all the methods for all 1,000 subtypes. So in that case, we currently use a heuristic for this. In that case, that's an upcoming work item that you'll see. We want to be able to support that, but there'll have to be some kind of a configuration option or annotation for that. So you can tell us, no, really, I really want you to compile this for all 1,000 types. So that's kind of a work in progress. Here's sort of a to-do list of some stuff that we have done over the past year or so, and then things we will do hopefully soon. So yeah, getting JLLs working was a big one, because there, of course, that's any binary dependency you have, that has to work, and they didn't work initially, but we got them working. So yes, handle some of these sum type things, which was a big roadblock for a lot of applications. Another big issue was the show function, because anytime we print something, we usually tend to print its type. And printing types, it turns out, is very, very dynamic, and itself very not type stable, because types have basically untyped vectors inside them of their parameters, so we don't know anything about what is in there. And basically, we don't specialize the printing code on every type, even though we could, because that just seems pretty excessive. So we don't bother to do that. So we had to write a basically statically typed version of this, so you have a fair shot at being able to actually print something, which people often want to do. And then supporting finalizers, that was an interesting one, because when you register a finalizer for something, the function is not called at that point, obviously. It means that function is going to be called by the runtime sometime later, right? But so that means we need to include it in the binary, but there's no call to it in your code, right? So that requires a special case. And it actually has to be done pretty carefully, because one way I thought we could implement it is, okay, when you see a call to finalizer, just pretend the finalizer is called at that point, right? Just like as if there was a call there. That might be how you might do it, but it turns out that doesn't work, because if you do that, then the compiler, the optimizer, thinks that thing actually is called in there, and then it assumes that sort of those things are happening at that call site, but you don't want it to make those assumptions because it's not really true. So it's not very accurate to tell the compiler that call is happening there. So you want to handle it a little differently. So it's a little bit subtle. Another cool thing that Gabriel and Cody added was basically automatic JL init. So this makes using libraries way, way nicer, because you don't have to tell someone, oh, by the way, before you call our functions, you have to call JL init. Very annoying. So now it's basically automatic. You can just give someone, libm written in Julia, they call sign, and it just automatically works, which is really, really cool. So yeah, that was cool. And of course, we've got CI now for both correctness and size. So if this of course has happened. If the hello world binary gets bigger than a certain size, we want CI to fail, so we have that now. And this is going to be released, it's still labeled experimental because we're not sure about some of this design, but it's going to be released in 1.12, and it's labeled experimental, but it's totally usable. So yeah, a few things upcoming that we need to do. So weird standard in doesn't work, which might seem like a pretty weird omission, but libraries don't really need to read from standard in, so it just hasn't been very important. Tasks are very similar to finalizers, and we just have to do the same thing for tasks that we did for finalizers. And yes, this configurable sum type limit that I mentioned. I think also the logging is also very, very dynamic. It turns out we have a very, very complicated logging system, and it doesn't work with this, unfortunately, so we have to find some solution to that. And tooling. So if you saw Shuhei and M's talk about the new language server, that is perfectly suited to helping with this. So basically there will be a mode where you can say, okay, I would like this to be trimmable, tell me everything in my code that makes this not trimmable. And it's a very similar analysis. But it's actually not exactly the same analysis that you always want, because like, for example, sometimes you care about type stability. But type instability actually by itself does not prevent something from being trimmable. So you want a slightly different tailored analysis for that particular problem. And also, so there's this JuliaC script, which for now is just sort of awkwardly stashed in the contrib directory, which is not great, but that's just sort of a place where you can find it for now. We should figure out some better way to package it and properly install it. And it's basically, it's similar in spirit to what PackageCompiler does. PackageCompiler is basically a thing that builds artifacts with a kind of API type of interface, and JuliaC does it with a command line interface. They should have basically equal functionality, but just different style of interface, so they should be basically fully combined into just one thing, or if you can either choose to use it from Julia or from the command line, as you prefer. And yeah, if you're generating libraries, you probably also want to generate header files for people. So generating header files or whatever binding code is needed for the calling environment would also be very, very nice and convenient. And then, of course, the build infrastructure. So you can, if you want to write a native library in Julia, you can automatically get builds going on GitHub. So that's a bunch of stuff we have to do, and there's, yes, a lot of good hackathon items in that list. So, all right, more broadly though, yeah, what's next for binaries? So in maybe, I don't know, hopefully next year, maybe in a couple years, if I were to add to that series of commits in the beginning about improvements to building binaries, so some things that are coming up is being able to basically get a private copy of the runtime with your library, possibly statically linked into it. And we've got some hacks in objectfile.jl that now make it possible to do that. And that's useful because you can get something that's hopefully more self-contained. If you can give someone one file, that's better than giving them 2 or 3. And also you can load more than one of them in a process. So if you build one of these and you try to load this in a Julia runtime, it will not necessarily work if you try to load more than one of them. Because each one sort of thinks it's a system image on some level. So the system image expects to be kind of the only one in the process. So you can't have more than one. But if you give each one of these its own private copy of the runtime, then in its own little world, it thinks it's the system image and it's happy. So that lets you do this. But it's pretty primitive because you have to basically interact with them using ccall, which is pretty unusual to call Julia with ccall, but that's how it would be. But it does at least get you these things. It at least gets you these things for a little while. Another thing we're planning to do is just use compression on the system image data, which should be sort of an easy win. And in fact, it's mostly implemented already. And of course, just ongoing work on shrinking the footprint and making more things in the language work. And I think it's possible there could be different ways to do trimming. So this is just complete speculation, but I think there will probably be a lot of programs where the call graph control flow based version is just never going to work because it's just too dynamic. And I think there are other things you could do. Like for example, basically look at all of the identifiers that are referenced in the program. And as long as you never try to fabricate a symbol by constructing a string and evaluating it, as long as you never do that, we might be able to figure out that certain entire types or functions are never used and we can remove those. So I think that might be an alternate approach that could be possible. It would be nice to have to do some experiments on that and see how well that works. And then the really big item, the one I'm kind of excited about, is the prospect of implementing kind of real separate compilation, where you can have separately compiled Julia code, but that will share a single runtime, which is better in many ways. And this actually we don't have this feature yet, of course, but it's actually slightly underway because Jameson put in this very under-the-radar, inconspicuous commit that basically doesn't change anything user visible at all, so I don't expect anyone would have noticed this. It's very under the radar, where he basically made every method in the system is now inside a single data structure, where they used to be kind of sharded out among types and everything. Now they're in one data structure. And well, why does that help? Because if you're going to have really separately compiled things, in the Julia world, what that means is each artifact has its own completely isolated view of what methods exist. So those need to be totally isolated from each other. So one of them could be using like a totally different definition of integer plus than another one, and they wouldn't interfere with each other, right? So that means you need to have all the methods that exist encapsulated in one object. And so that has already been done. So that is actually one step along the way, and that's done. So we're getting there. And yeah, you would basically, if we have these, you would load and invoke them just like ccall. So you can do it now with ccall if you have one of these @ccallable entry points. In the future, it'll be like some kind of invoke type of command, like invoke inside compilation unit kind of thing. So if you know about what we do now with these so-called frozen worlds, where sometimes we run code in a fixed world where it can't see new methods, this is basically a general version of that that's far more usable and scalable. And yeah, you'd have, with a shared runtime, you'd have a shared GC heap, shared thread scheduler, so much more efficient. They could even reference each other's objects and so on. So this is kind of a goal. I don't think it's super hard to do. I think it's doable. I hope we get this pretty soon. And then, of course, there's some stretch goals, like doing things like cross-compilation and targeting different kinds of platforms. And these are very speculative sorts of things. So this is kind of what I'm thinking about. And that's it.
Very exciting talk. Are there questions?
Hi. Was just wondering if you could also add to the to-do list. So you added some extra code for JL init, so you can use it as a shared library on C++ or whatever. See? Could it be possible to do a similar trick so you can generate Python extensions and MEX files?
Yeah, I mean, so everything can call C, so yeah, you can eventually make that work, yeah.
Well, those are special entry points used for Python extensions and MEX files. That will be quite useful, so you can just start building libraries for Python and MATLAB, but in Julia.
Yeah, I think adding nice Python and MEX interfaces is just a matter of sort of grinding it out, because once we do this, it just becomes like calling C.
Okay, thanks.
Others? Yeah, I wanted to ask if there's a possibility that in places where there's type instability, you don't know which methods are going to be called in a certain place, that you can add some sort of profiling mechanism to the static analysis, so that you basically say, I know what's statically reachable, but in the places where I would usually give up, I know from this test run that only these 3 types appeared in this place, and so I'm just going to use those and fail for the rest.
Yes, so you can do things like that. Actually, one thing you could do is take your precompile statements and just search and replace precompile to entry point, and then we will include all those things. So that might include more than you need, but it will take care of anything that was in your profile run will then be included. And so you could do that, and we have the trim unsafe option, which it does exactly the same thing, except we just don't print any errors. So if you're very confident that you've covered everything that's needed at runtime, then you can just turn off the errors and we'll just generate it anyway, and you can try your luck. So it is possible to do things like that. And there's a whole bunch of things you can do with type unstable code. Like sometimes we will actually turn a call site into an if statement where we break out some cases, or there are all sorts of things you can do to make some of those cases work. But yeah.
Did you want to comment on the dynamic dispatch tracing that got added in the upcoming 1.12 and whether that integrates with the trim option yet?
Well, I think that's similar to like the precompile tracing, or yeah.
A missing feature that we talked a little bit about this is basically a localized unsafe. We've talked a little bit about this, like say, oh, I want everything to be safe, but I know that this specific place is giving an error. You put like add ignore or something on that function, and it then when it's verifying, it says, okay, this function the user said they don't care about it, and then potentially it makes the experience a little less unsafe. It's still, and by unsafe here, what happens is if the method isn't found, it throws a method not found error. So it's not going to necessarily blow everything up. It's a pretty well-defined behavior what happens when you don't have the code.
Excellent. And I think we have time for at least one more.
Yeah, thank you for the nice talk. So I've actually been trying for a while to, we have some nice Julia code and we want to make it accessible to our colleagues, and so I want to wrap it in some, let's say, pip installable kind of package. And one thing I've noticed during the last months is that it's for me always actually quite unclear, what you can do and what you cannot do yet with the Julia C, and so you always end up kind of implementing something and trying it out. And actually the runic .jl was kind of one example where you can see which you wrote as kind of a nice reference point to see what is possible. But I would really love if there was maybe one kind of reference program like runic, and then maybe going forwards, just as kind of a sort of documentation to see what is already possible, and also what kind of a reasonable build process would look like, getting this kind of Julia to Python or to C or whatever. So this is maybe more like a wish or a request or an appreciation for the documentation is already there, and yeah.
Yeah, no, yes, totally, yeah. Recipe books are always good. We should have recipe books and as much automation as possible, and it's, yeah, it can be a little bit hard to predict what will work, but we have, the growing list of like common pitfalls, things to look out for. Is kind of all you can do for now.
All right, with that, just for the reasons of time, we should call it quits. Let's all thank the speaker again, and he'll be around, so feel free to ask more questions then.
Thank you, Tim.